In this demo, we showcase Northeastern University's AI-based spectrum sensing and sharing developed within the AI for RAN working group. The goal is to demonstrate how the radio access network can operate as a distributed RF sensor, enabling real-time spectrum sensing and AI-driven signal classification. Starting from our system model, we leverage the O-RAN paradigm to deploy a disaggregated RAN made of different distributed units connected to a common central unit, and we connect them to different dApps performing real-time sensing. The dApps are software programs that enable real-time RAN observability and programmability. They are directly onboarded on the RAN infrastructure and can access with sub-millisecond latency user, control plane, and privacy-sensitive data that is not available at the RAN Intelligent Controller, or RIC. This enables local AI-driven control based on real-time radio conditions. In our deployment, a sensing dApp is connected to a GMB base station powered by an open-air interface, which provides connectivity to the mobile devices. Within the same spectral environment, we have introduced an external RF source that may represent either an incumbent user with priority spectrum rights, such as Federal Radar System, or an international jammer attempting to disrupt communications. Through the dApp and the E3 interface, we extract user plane IQ data that is not available to the near real-time RIC. In this demo, sensing is performed over non-scheduled slots to detect external RF sources. A pre-trained convolutional neural network processes the signals and classifies the spectrum condition, distinguishing between clean spectrum and the presence of external emitters, such as radar or jamming signals. The sensing dApp is not limited to classification only. Using real-time inference results, it can also trigger control actions at the GMB. In this example, it performs the physical resource block masking so that the MAC scheduler avoids allocating transmissions over the affected frequency resources. The same dApp-based framework also supports data persistence and more advanced AI-driven pattern analysis to enable spectrum awareness within the O-RAN architecture. The goal is to go beyond classification based on a supervised approach, and thus limited to a specific set of interference sources. To do this, after the classification step, the system outputs not only a label, but also a confidence score. This score is used for out-of-distribution detection. It provides an indication on whether the observed IQ samples match the expected signal distribution. Samples that fail this check are stored in an unknown buffer and later processed during clustering phase. This phase determines whether the unknown signals can be mapped to existing RF embeddings or represent new signal signatures. Spectrum awareness is therefore achieved either through confident classification or, when confidence is low, through structured characterization of unknown signals. With enough validated samples, new embeddings can be added to extend the model's classification head. In this clustering view, the interface summarizes RF signature discovery and shows the parameters of the detection pipeline, including group-level signal analysis. The system explains why a discovered cluster is accepted as a new embedded or rejected based on statistical and feature space criteria. Finally, we demonstrate how information produced by dApps can support coordinated control across multiple GMBs. An XApp running on a near real-time RIC reads dApp sensing reports and determines whether an incumbent or interferer is degrading the GMB UE link. When needed, it triggers a handover toward a cell operating on a different center frequency that is not affected by the interferer. Because sensing is continuously updated by distributed dApps, the XApp can adapt decisions dynamically and maintain robust spectrum sharing across heterogeneous radio technologies. Thank you for watching this demo. We look forward to continued innovation enabled by dApps in intelligent RAN systems.